What's up, Raiders? In this video, I want to build off of the work we already did, analyzing a level 2 cliff scenario. Level 2 meaning that the ball, instead of just being dropped like a level 1 problem, is either being thrown vertically up or vertically down from the edge of the cliff. So if you remember, we did an earlier example where we focused on analyzing it algebraically, and I have up here on the screen when we set up an equation to analyze the ball thrown from the top of a 75-meter cliff, and it was thrown upward at 10 meters per second, and gravity is pulling down at the entire time. How much time would it take to hit the ground? Well, we talked about when you have an equation like this, it's quadratic, and you put it in standard form of ax squared plus bx plus c equals 0, how you could certainly do the traditional calculation with the quadratic formula to figure out what values of time would make this equation true. In the real life application of this, that means when the ball will have reached 75 meters below where it was thrown, in other words, when it would hit the water. And there's nothing wrong with that, but it's certainly time consuming. So you can use a simple program on a graphing calculator, or there's various things you can find online for free that'll do that calculation for you once you put your equation in standard format, where your a value is the coefficient of the squared term, your b value is the coefficient of your unknown, and then your c value is your constant. So when we did that, we got that the time for the ball to hit the water was 5.06 seconds. So I want you to remember that, because when we go to Desmos, you're going to see how that'll show up in the graph later on. And then we also analyzed this scenario, the ball being thrown up from the edge of a 75-meter cliff, to figure out some characteristics about its peak when it's at its maximum height, because at that exact instant, it's not moving. And so we were able to figure out, using VF equals VI plus AT, we were able to figure out that the ball would reach a final velocity of 0, not final velocity ever, but for analyzing up to the peak at that instant, its velocity was 0. If it went up at 10 meters per second and gravity is pulling down and slowing it down at a rate of 9.8 meters per second on the way up, it would take 1.02 seconds to reach its peak. And building off of that, we're also able to figure out, well, how much higher would the ball go in this 1.02 seconds using VF squared equals VI squared plus 2AD. And when we did that, we calculated that the ball would go an additional 5.1 meters up. So adding that to the original height of 75 meters above the water, the ball would be 80.1 meters above the water at its peak. So keeping those numbers in mind, let's now take a look at if we analyze this more from the graphing perspective. So let's go to Desmos.com, or you could use the Desmos app. It's simple enough. Go to Start Graphing, and then we're going to enter in that quadratic equation that's in standard format. So it was the negative 4.9 t squared plus 10t plus 75 equals 0. This is set up in order to figure out when the ball, when it's launched up at 10 meters per second, when will it ultimately end up falling down to 75 meters. So with that equation, when we go to enter it into Desmos, they don't have t for the variable, they have x, so that's easy enough. So it's negative 4.9 x squared plus 10x plus 75. So it gives us this parabola. And there's several critical points in the graph here that, if you remember when we talked about the algebraic analysis results of this, you should recognize some critical values on the graph. So if we find the y-axis for this parabola, we'll see it's at 0, 75. Well, if we think about what this graph really is, the x-axis is representative of time, and the y-axis is representative of height. So at a time 0, the ball is at a height of 75 meters at the edge of the cliff, meaning when we started. Now, if we look at the peak, we'll recognize these values. The coordinates of this vertex here at 1.02 seconds, which we know that was the time of the peak, the ball reaches a height of 80.1 meters. And then another critical point, find one of the zeros here. So you can see this point here, at 5.06 seconds, the ball is at a height of 0 meters. That's when it hit the water. So hopefully you can see the variety of ways you can do these kind of things. So if you have any questions, like always, contact me, Raider Nation.